Good morning. All right, today we are continuing in chemical bonding with polarity. So we've actually already been introduced to polarity when we were looking at the differences between covalent and ionic bonding, where we know that covalent bonding is a sharing of electrons and ionic bonding is a transfer of electrons. However, there is also kind of a middle ground that we need to talk about today, which would be polar covalent bonds. When we're going through this, I want you to remember electronegativity and our definition for that, and how we compared electronegativity as a tug of war of atoms on the electron. So recall that electronegativity is the tendency of an atom to attract electrons in a bond. And when you're looking at ionic versus covalent, you can look at the difference in electronegativity to determine between these two types of bonds. However, as we discussed earlier in the unit, bonding isn't simply dichotomous. It's not purely sharing or purely transferring. To be honest, it's more of a spectrum. There can be bonding in between. And what can happen is you can have perfect sharing of electrons, right? You can have the perfect transfer of electrons, or you can have unequal sharing of electrons. So that unequal sharing of electrons is what we call polar. And in that case, one atom can have more pull on the electrons than another. So, where if you have equal sharing, this would be like two people of the same size in a tug of war, right? Transferring would be basically throwing the electron from one atom to the other. And unequal sharing would be like a tug of war between the Hulk and, a 10-year-old scrawny kid. Okay. All right. So with polar covalent bonds, the word polar implies that poles. Poles like North Pole and South Pole of the planet. Two opposite ends of something. In a polar bond, there are opposite ends to the bond, because what's going to happen is you're going to have a slightly positive and a slightly negative end to the molecule. So let's back up. For a polar covalent bond, what happens is one atom has a higher electronegativity than the other atom. And in that case, the electron is going to spend more time with the more electronegative atom than it will with the less electronegative atom. So again, if we're talking about a tug of war, this is a terrible drawing, but between the Hulk and a scrawny kid, right? The Hulk would be the more electronegative atom, and the scrawny kid would be the less electronegative atom. And in this case, the electron is going to spend more time with the Hulk, with the more electronegative, because it's stronger and it has more pull on that electron. Okay. Just a reminder of what the electronegativity values look like. As you should recall, fluorine is the most electronegative with a 4.0. The least electronegative atoms are at the opposite end of the periodic table. Francium and cesium down there with 0.7s. This is a throwback to periodic trends, so as you can see, we've labeled the trends on this table for you. Okay, great. So let's again look at just kind of what a polar bond is. So to determine polarity, again, you have to take the difference in electronegativity values. So delta En equals what? Where delta is difference, so that implies subtraction. Now, the molecule that we have here is water, H2O. When you're looking at a molecule, you have to determine bond polarity. So you need to actually isolate one bond at a time. So we're going to look at one HO bond at a time. And I've got the electronegativity values listed here. So we have oxygen with 3.5 and hydrogen is 2.1. So when we do that subtraction, it's just going to be 3.5 minus 2.1 equals 1.4. Okay, so this is the difference in electronegativity. We're going to call that the dipole moment, which we'll get back to in a moment. This is a fairly large difference, which means that water has very polar bonds. And Water having polar bonds is actually what gives water its really unique properties, which we'll talk about tomorrow, but it makes water cohesive, adhesive, um, viscous. It gives it, makes things wet, it makes droplets, it has high surface tension, things like this. So we can talk about that tomorrow. Okay, when we're looking at polar bonds, we can label these on Lewis dot diagrams to show or imply polarity. And we're going to continue this tomorrow, but we'll keep working with this water example. So we use this term dipole moment to imply the magnitude and direction of a polar bond. So the dipole moment is the actual value of the difference in electronegativity. So when we were looking at water, for example, right, here's water's Lewis dot diagram, we determined that the difference in electronegativity there was 1.4. So the dipole moment magnitude would be 1.4. All right, and when you're looking at that magnitude, if you have a large dipole moment, we say that bond is more polar. So if you're on this spectrum here, more polar would be more towards, the transferred side, right? More polar is over here. And then less polar would be more towards the sharing side. All right, but all of this middle ground here would be considered polar. Okay, the distribution of electronegativity in a bond can be depicted using these little partial charge signs as well. So if you look here, this delta plus, that little squiggly thing is a lowercase delta, and it means partial. So partially positive, partially negative. You can also label the direction of a dipole moment using that little arrow with the plus sign. The arrow, the way that works is that the actual plus side goes over the less electronegative, and the arrow points towards the more electronegative atom. So again, let's put this into practice. All right, so we have the water molecule. Water has two HO bonds, so we actually have to label both of those bonds. Okay, so I'm going to first label their dipole moments. Now, I know that oxygen is the more electronegative, so that's going to be where the electrons want to go. So when I'm looking at this, the way I would draw the arrow is I'd draw the arrow along the bond direction, and I'm going to put the arrow head towards oxygen, because that's, again, the more electronegative. And then the plus side goes over the hydrogen like that. So that's how you draw a dipole moment for a bond. And I can do the same thing for the other HO bond. Okay, so I've just labeled my two dipole moments. These are hideous arrows. Okay, that's how you do that. Now, if I wanted to label the partial charges, those little delta signs, go over the atoms themselves. So the more electronegative gets the negative side, so that would be oxygen. In both bonds, in both cases, oxygen is negative, and the hydrogen is positive. So I'm going to put that little squiggly side over the hydrogens like that. So I've labeled both the dipole moments and the partial charges of water. Okay, and again, you can do that for each bond. All right. Electronegativity ranges. This is very important. And this is something that you're actually going to have to memorize for the Regents exam, because they don't give these parameters to you. Okay, so if you are calculating difference in electronegativity and you see that you have a very small difference, anything from 0 to 0.4, we say that that is nonpolar, meaning that we can say that those electrons are shared equally. All right. If the difference in electronegativity falls somewhere between 0.5 and 1.7, we say that those bonds are polar covalent. So again, if you're looking at my little spectrum thing here, this middle region of the spectrum where you have somewhere between covalent, somewhere between purely ionic, that's all polar covalent range, and that's where you have unequal sharing. Somewhere between pure transfer and pure sharing. If the electronegativity difference falls far out of those bounds, so anywhere greater than 1.8 or equal, then we say that those are ionic. So that would be pure transfer. There is no sharing at that point. One important exception to note is HF. HF, hydrofluoric acid, is the only covalent molecule that has an electronegativity difference over 1.8. So between fluorine and hydrogen, I believe it's 1.9. It's an extremely polar bond, and that's also why hydrofluoric acid has such unique properties, which we will discuss in the acid-base unit. Okay, so what we have here, these are electron density diagrams, and as you know, density shows kind of how closely packed, or basically the mass per area, mass per volume of something. So when you're looking, it's comparing the three different types of bonds here. You've got nonpolar covalent, polar covalent, and ionic. Notice in the nonpolar covalent you have two spheres of equal sizes, which implies that A and B are sharing the electron evenly. The electron is spending equal time around both A and B atoms. Whereas in the polar covalent bond, you can see that these spheres, the electron densities are clearly different, which is showing that the electron is spending different amounts of time around the atoms. And because B has a larger sphere, that shows that the electron is spending more time around atom B than around atom A. From that, we can then conclude that atom B is going to have a higher electronegativity than atom A. Okay, so B would be labeled the partially negative side if I was going to do that. Whereas with the ionic, finally, these spheres are also very different sizes. They're also not even touching, which implies that the electron is not shared. It's actually completely transferred here. You also see that from, again, the sizes of the spheres, B is more electronegative than A, which is why B has the negative charge and A has the positive charge. Okay, and finally for practice, I just want you guys to calculate the difference in electronegativity for these atoms and determine if they're polar or not. So again, tomorrow we're going to be looking at molecular polarity. You guys are going to be going through a simulation on the computer, which I will open up today, but will be due tomorrow. So please be sure that you are looking at that, and if you have any questions, please feel free to email me. Good luck.